Okay, so at the end of the last video, I was explaining some basics about scientific notation. And basically, it's just that every time we multiply by a power of 10, we move the decimal place to the right one time. So in this example here, 3.69 times 10 to the fourth means we move the decimal place to the right 4 times. So we've got 3.69. We're going to move that 1, 2, 3, 4 times. And we use zeros as placeholders, and so that becomes 36,900. Okay, and so to go the other way around to think about it, if we're converting this to scientific notation, usually we want to put the decimal point immediately following the first digit in scientific notation. So we would want to move this decimal place 1, 2, 3, 4 to get it immediately following the 3, and since we moved it 4 times, then that's 3.69 times 10 to the fourth. Now, when we take 10 to a negative exponent, like 10 to the negative fourth, what we're saying in that case is that we are dividing by 10 4 times. So if we had just for example here, let's say we had 3.69 times 10 to the negative fourth, we would have our 3, our 6, and our 9. But if it was times 10 to the negative fourth, we would move that decimal place 1, 2, 3, 4 times, and then we'd have to have 3 zeros as placeholders. So that becomes 0.000369. So hopefully you've seen scientific notation before in some other class, and this is just a review. Again, I'll have additional resources on Blackboard, some Khan Academy videos that go over this. So if you need a little bit more of a refresher, check those videos out. Okay, let's do some practice exercises here with scientific notation. We want to write each of these in scientific notation and state the number of significant figures. So if we look at the first one here, again, when we put things in scientific notation, we want the decimal place to come after the first number. So we want this to be 2.58. So I'll write it over here, 2.58 times 10 to the something. Now, what is that something going to be? So it goes 1, 2 decimal places here. So we're moving it to the left. If we start with our decimal place here after the 2, we would have to move it 2 places to the left to get over here. That's negative, that's dividing, so it would be to the negative second power. Oop. All right, let's see here. I'm going to erase this and write it a little further over to the right because I didn't anticipate how much space that would take up. Okay, with some quick editing, I moved that number over here, 2.58 times 10 to the negative second. And again, the question is how many significant figures are there? There are 1, 2, 3 significant figures. So let's check and see if that's right. 2.58 times 10 to the negative second with 3 significant figures. That is correct. All right, let's look at the next one here. So we have 42,300. The decimal place is not written, but it is implied that it exists right there. And we want to move it over here. We want it to be 4 point whatever. So we're going to have to move that over here. That was 1, 2, 3, 4 times. So we'll end up with a 4.23 times 10 to the, what, it was 1, 2, 3, 4 times we had to move that to the fourth. Okay, now you'll notice I wrote 4.23, not 42300. There was no decimal place written here. So since there was no decimal place, the trailing zeros are not considered significant. So it has 3 significant figures. And we'll check our answer. 4.23 times 10 to the fourth with 3 significant figures. Excellent. Now let's look at the last one here. Again, we want to move this decimal place to be after the very first number. We're going to have to move it over 2 times. Okay, so we're going to end up with 3 point what? 4, 4, 5, and then what about this 0 here? Is this significant or is it not? Well, again, the way I think about it is the person writing out this number, they didn't have to write it there. It's not really a placeholder. We could have just written 344.5. And 344.5 and 344.50 has the same value, but somebody took the time to write that extra 0 there. They added it for a reason. That makes it significant. So we are going to include that 0 here. Times 10 to the, well, we had to move it 2 times. So it's to the second. And there are 1, 2, 3, 4, 5 significant figures here. Let's check that answer. 3.4450 times 10 to the second, 5 significant figures. Okay, that does it for significant figures. Let's move on now to units. So again, scientific method is all about testing hypotheses, and we typically test things by measuring them. And so we need to understand units of measurement. Now, in the scientific community, the metric system is used. As an engineer myself, I like the English system. I'm used to pounds and feet and kips, and so it can be tough to wrap my mind around these metric units. But it's really helpful if you can kind of visualize how big something is or how much mass something has in the metric system. So to familiarize ourselves with some of these units of length, we have some examples here. The standard unit of length that we are going to be using for all of our problems is the meter. It's about 3.28 feet, so it's a little bit longer than a yard. The exact conversion is 1 inch is 2.54 centimeters, and 1 kilometer, 1,000 meters, is about 0.62 miles. So you can, the way I remember it at least, is that 60 miles per hour is approximately 100 kilometers per hour. Now, if we look at smaller units of measurement, we have millimeters. That's 1,000th of a meter. And if you want to visualize what 1 millimeter is, it's about the width of the tip of a pencil. Crayon is a little wider. That's about 2 millimeters. And the opposite end of the pencil, the eraser end, is about 5 millimeters. That might help you visualize a little bit. Centimeters is 100th of a meter, and 1 centimeter is about the diameter of a pea. A peanut is about 2 centimeters long. A walnut is about 4 centimeters, and a lime is about 5 centimeters. So that just kind of helps you visualize these different lengths that you may not be too familiar with. The unit of mass, and mass is basically how much stuff something is made up of. The unit of mass that we are going to use is the kilogram. So although a gram is technically the base unit, a gram is very small. A paperclip has a mass of about 1 gram. So most things we're going to be dealing with are going to be significantly larger than that. So rather than dealing with rather large numbers and potentially a bunch of trailing zeros, we tend to stick with the kilogram. So we're going to be using kilograms as our primary unit of mass. And 1 liter of water is 1 kilogram. It has a mass of 1 kilogram. That's about 2.2 pounds. But at this point, I need to point out that mass and weight are not the same. Now, I may, throughout the semester, accidentally say that something weighs a certain number of kilos, and that's not technically accurate. kilograms are units of mass, how much stuff there is, not the same as weight. So the traditional way of pointing this out is that weight can vary depending on gravity. So if we think of the astronauts that went to the moon, when they landed on the moon, they had significantly less weight. They kind of floated in the air. And that's because the moon has much less mass and therefore much less gravity. So weight is affected by gravity. Weight is a force. Force is equal to mass times acceleration. So if we're talking about the acceleration due to gravity, weight is the mass an object has multiplied by the acceleration due to gravity. So that can change depending on the gravity and where you are in the universe. If you're on Earth, your weight is different than it would be if you were on the moon, versus if we were somehow able to go to Jupiter. Jupiter is much more massive, and therefore your weight would be much more. But your mass is always going to be the same. Mass does not change. Mass is not dependent on gravity. So we're going to talk primarily throughout the class about mass and not weight. Okay? Units of time, fortunately, are the same in there is no difference between the metric system and the English system. Time is time, and the standard unit of time we will use is a second. And as I'm sure you're all aware, there are 60 seconds in a minute and 60 minutes in an hour. So if we use scientific notation, we're going to end up multiplying numbers by 10 to some power, like let's say 10 to the third. Okay, except it's kind of a mouthful to always be saying, 3.4 times 10 to the third grams. It's simpler to use a metric prefix like kilo. You could say 3.4 kilograms. So the metric system has all of these different prefixes and their abbreviations. This one here, micro, this abbreviation is mu. This is the Greek letter mu. Okay, and I always try to tell my students to actually think in terms of the Greek letters. Don't just think of that as like a squiggly M or a weird looking M, because then you might confuse that with milli. It's mu. Think of it as mu, and then you're not as likely to get it confused. So we can use these prefixes in place of having to say all the time what these values of 10 to the whatever powers are. And the ones that we use mostly are going to be towards the center of this list. I would say between here. These are the most common. Kilo, hecto, deca, deci, centi, milli. Kilo is 10 to the third, or 1,000. Hecto is 100. Deca is 10. Deci is 1/10. Centi is 1/100th. And milli is 1,000. Now, with advances in technology, we have become more familiar with some of these smaller and larger prefixes. For instance, giga, like gigabytes, when describing the size of a computer hard drive, or even tera. There are hard drives now that are in the terabyte range. Before too long, we'll probably be up to peta. And then perhaps someday in the far future, we'll have exa, zeta, and yada. On the small side, micro. Micro is just sort of synonymous with being small. Same with nano, like nanotechnology, nanobots, nanofibers. And potentially in the future, we will see pico, femto, and atto added to our everyday usage. So you don't necessarily have to have all of these memorized, but you should be able to refer to them. They can be found on the inside cover of your textbook, which I have scanned and posted to Blackboard as well for your reference. So it looks like I'm about out of time again. We'll pick this up in the next video.